Hi everyone, my name is Alex Kingsby. I'm from nLIGHT. Today we're going to have Aconity3D talking with Aachen University. Aconity3D has been a really instrumental partner for nLIGHT. They were one of the first OEMs here in Formnext, in additive manufacturing, to integrate the AFX laser. So they know a lot about beam shaping. And thankfully they're supported really nicely by Aachen University. Today we're going to hear from Martin Buscher, who is the head of job shop and testing from Aconity3D, and also Max Rommerskirchen. He's from Aachen University. They're going to be talking about a case study in stainless steel. This case study is underpinned by a lot of really good research from Aachen University, but then Martin is also going to talk about the way to implement the case study, right? So implementing the research and making a real case study out of printing stainless steel. Thank you. Thanks, go.
Thank you, Alex, for the introduction, and thanks to Rob and nLIGHT for having us here. I'm Martin Buscher from Aconity3D, and together with Max Rommerskirchen from Aachen University, I will tell you a little bit about how to gain productivity with the AFX for processing of stainless steel. And first, Max will talk a little bit about the study they carried out with our machine at the university with the AFX laser inside.
Yes, thank you very much. I hope you can hear me loud and clearly. Perfect, thanks very much. And thanks for having us. Maybe I start with a short introduction. So my name is Max Rommerskirchen. I'm actually working at the chair for digital additive production at RWTH Aachen University. And I think it was 6 years ago when I first came in touch with laser and powder and the interaction of all these components during my time at Fraunhofer Institute for Laser Technique. There I mainly focused on geometry adaptive process control. And since last year, I'm leading the group for so-called Advanced Additive Manufacturing, where we are mainly focusing on different topics in the field of laser powder bed fusion, as well as metal binder jetting technology. And they were working on different projects in the field of process control or monitoring, multi-material additive manufacturing, combining two different kind of technologies. But also, if we are talking today about the topic of an increased productivity, we are working with the nLIGHT laser technology. So for an increased productivity while maintaining a certain level of quality. And that's what we actually did within the last research work we had at our chair in Aachen. Yes, perfect. Maybe if you just push one more. Yeah, perfect, thanks. As you can see right here, what we did practically is more or less a black and white comparison between the Gaussian profile, the mode 0, as you can see on the left-hand side in the video. So regarding to the intensity distribution, we have the maximum power in the center, which decreases towards the edges. And then we made the same experiments, as you can see in the center and on the right-hand side, while adjusting the layer thickness and choosing the shape of the laser in the AFX mode 6. So here we have the comparison. In the center we have 30 microns layer thickness, and on the right-hand side we choose a 60 microns layer thickness to maintain a constant level regarding to the energy input we have. How did we do that? As you can see, that was a bit too fast, sorry. We started manufacturing simple test geometries like bulky parts, as you can see on the left-hand side. And there we varied the amount of energy input into the powder bed. So we varied the laser power, the scanning speed, as well as the hedge distance. And then in the end, for sure, we did a lot of post-analysis. So we took a closer look on the cross-sectional area, if we can detect any types of porosity or cracks within the part. And the good point is, if we skip one more forward, is that we can see we could increase the build-up rate up to 650%. So the starting point, if you take a closer look on the Gaussian profile, was that we had a value of almost 2 cubic millimeter per second, and we could increase that while doing this adaptive beam shaping up to almost 15 cubic millimeter per second. So we are talking about an increase of 650% right here. And if you compare those volume densities, we have at least a relative density of 99.5%, which is quite good, especially regarding to quality assurance. What I need to say is all the experiments we run on an Aconity mini machine, which is equipped with an nLIGHT laser with a maximum power of 1.2 kilojoule per second. And here we have the opportunity and the possibility to adjust our beam shape coming from the Gaussian profile if we are talking about precise parts, filigree structures, or thin wall structures, but we can also widen our beam shape up to 340 microns in diameter if we are going for an increased productivity. Regarding to the machine itself, in Aachen, this machine is also equipped with some kind of process monitoring technology. So we are mainly playing around with, for example, an optical tomography camera, but also with a pyrometry system in order to evaluate the heat analysis in every single layer. So with this technology, we can detect also different kind of hotspots, which could lead, in the worst case, to a part failure. And after the job, we are also doing some offline process monitoring. So we try to transfer these two-dimensional data into a three-dimensional level and compare the original geometry with the produced geometry. So that's what we did in the first instance. There you can see, just as a short summary of our experiments, so we could increase the build-up rate up to 650%, and then for sure we calculated also what does it mean regarding to costs. So there we've mainly focused on the duration of the process concerning the melting process as well as the recoating process, and there we chose like a simple geometry, a very simple build job, a typical build job for the LPBF process, and there we saw that there's a reduction of the process duration of about 78%, which is quite good. But I'm pretty sure, Martin, you also brought a certain application from the industry for us to talk about all the economic influence we have while using this adaptive beam shaping.
All right, thank you, Max. So yeah, what we wanted to know as a company who also manufacture parts is how much can we decrease cost if we switch to these higher build rates. And as an example, we have this part here, which is a cooling plate we put into our own heating devices in our machines. So it's a stainless steel plate with cooling channels printed, and the part as it is has a volume of roughly 3 liters. And now we calculate 3 different cases. If we manufacture it with a standard 60 micron process, how we have done it before, and if we manufacture it with the AFX 90 micron parameter set developed by the DAP. And also if we check on the part design and see how we further can decrease the printing time and the cost. And this is done by having a better look at the part geometry itself. So it's a plate, it's quite simple, but with the cooling channels. So the actual benefit is that we can print these cooling channels, but we don't want to consolidate the whole material. So what we make is we split the part in 2 parts. So we mill a base plate, which has all the mountings, all the threads for putting it into the machine, but then printing on top of it the actual additive value. And so we can decrease the volume of the part additionally from 3 liters to barely half a liter, which additionally saves us some time. And to put that a little bit in numbers, when we combine the new processing, but also the design for the manufacturing, we first have a look at the printing times. So we have the 2 process parameter sets on the left side, our standard 60 micron process with 250 watt, and also then the kilowatt process with 90 micron layer thickness with the AFX system. When we calculate then the printing time, so we have standardized time like preparation of the machine, we have the inertization of the machine and the recoating process, and then the actual melting process. And if we calculate that for all these numbers, we see that almost, if we print it completely with the old parameter sets, we need for one part 193 hours with a single laser machine. So you won't print that part. It's barely too long. But just by changing the parameters, you decrease it down to 74 hours and have the full consolidation of the 3 liters, which is a high amount. But still, you see that the laser on time is the highest peak of that composition of times when producing it. And to reduce it further, we have this smart design of manufacturing and decreasing it then down to 60.5 hours. And if you put that then in cost numbers, so we'd see that this barely translates, this 90% of time saving, nearly one-on-one translate to the cost saving. Because if you have an hourly rate of your machine and you can decrease it from nearly 200 hours printing time down to not a day printing time, you see that the part costs come down from $20,000 down to $2,000. And it's really just by changing the parameter set, maintaining the quality, but also by changing the design of a part, so having the whole process chain in mind. Of course, you need to manufacture the plate where you print on top, but if you need to do the threads, the milling, nevertheless, if you do it on the additive manufactured part, or if you do it beforehand, and saving a lot of printing time and part consolidation. Are there any questions regarding the numbers or regarding the process parameter set so far?
So Martin, can you speak a little bit more to that really profound reduction also in this design optimized configuration?
So I will just go back to the part. So the very first 50 millimeters of that plate are very simple. So we can just put it into a milling machine, making the whole part ready. We can mount it onto our machine, seeing where the part is mounted and orientating our actually additive printed value. And this saves us then the material to consolidate and makes the manufacturing much cheaper. And additionally, if you see we have this honeycomb structure to actually save some material. So you get the stiffness, you still get everything you need for the part, but you don't have to consolidate the whole material. And this is how to save the time.
Does the base plate require some special treatment on the surface or in the design in order to just start building on top of it? Or?
Yeah, we just need, so this is stainless steel, so we can use the very same material. So 316L also for the base plate, for the preform. And the only thing is that you need to have a grinded or a sandblast surface to start printing on that head. So thank you all for having us here and for your attention. And
thanks very much.
Great. Thanks very much, guys.
It's great.